Good morning, everyone. My name is Sally Ng, and I'm an associate professor in the School of Chemical and Biomolecular Engineering. I also have a joint appointment in the School of Earth and Atmospheric Science. So today we're here to talk about air quality research at Georgia Tech. So we have my colleague, Rodney Weber, Jen Kaiser, and Ted Russell. So Georgia Tech has a strong reputation in atmospheric science and air quality research. And you can see that many of us are from different departments in both College of Engineering and College of Science. So I will start with my own research, and then we'll go through each one of them to discuss more about our own research. So I study particles. So particles or aerosols. As you're sitting there listening to my talk, you're breathing in these particles continuously into your body. So these are tiny little particles that is too small to see. So we call them aerosols, or we also call them particulate matter, PM. So you might read in newspapers about PM 2.5. So PM 2.5 are particles smaller than 2.5 micron in diameter. Or if you're talking to a chemical engineer, they might refer to as atmospheric nanoparticles. So we are very interested in studying these particles, how they are formed, what are they made of, and how do they affect our health. So aerosols have tiny particles, but they have huge impacts on health and climate. So in terms of health, there are many studies that show that aerosols increase in these concentrations can lead to increases in disease, like cardiovascular disease and respiratory disease. And aerosols also affect the Earth's energy balance. So these tiny particles, depending on what they are made of, they can absorb or reflect radiation back to the space, or they can form seeds for clouds and reflect the radiation also. So they are tiny particles, but big impacts. And in my group, we study specifically aerosol chemistry. So many of these particles are actually not emitted directly as particles. So if you're driving behind a truck in the morning on your commute here, you might see these black soot particles emitted from the truck in front of you. So those particles are directly emitted as particle, and we call them primary particles. But in our group, we study secondary particles. The secondary particle does not mean that they are not important. They're secondary because they are formed from these reactions in the atmosphere. They're emitted as gas phase compounds. So I have a nice conversation with a gentleman this morning about how volatile organic compounds can get transformed in the atmosphere. So if you go to a pine forest, you smell really nice pinene smell. So that is a compound called alpha-pinene that can be transformed in the atmosphere to form these secondary organic particles. And in our group, we use several different approaches. So the first one is that we do chamber experiments. So the chamber is about the size of from this room to the end of the wall. And it is an atmospheric simulator, you can think of it. And it has 300 UV lights and also a temperature control environment. So what we can do is that we can actually put these VOCs into the chamber, and we can react and watch what compounds are being formed. So at some point, some of these compounds are going to be non-volatile. So thermodynamics will require you to go into the particle phase if you're non-volatile or semi-volatile. So if you have a particle around you, then you can condense onto these particles, that is existing particles, then you make this secondary organic particles. Or if you don't have any particles around you, you can nucleate and make your own particles. And so basically this chamber facility, you can think of it as an atmospheric simulation facility so that we can actually track the evolution of these VOCs all the way to the particles. And I don't have a video to show here, but our lab is featured on ESPN if you want to check it out. And the second type of work that we do is called ambient measurements. And so when I do ambient measurements, I often collaborate a lot with my colleagues in EAS and like environmental engineering. So we take all our instruments to the field and do measurements. So we travel to a site, we stay there for a month or a half, and then try to really understand the atmospheric chemistry and aerosol formation at that site. So all the instruments in our labs have wheels, so they're very easily portable to different parts in the world. And the reason we have to do this as a group is because each one of us will have a different instruments. So I measure A, you measure B, she measures C, and so together we can actually really understand the whole atmospheric chemistry. And lastly, we also work on the health effects. So one of the major issues of these fine particles is that they are not made the same. So a tiny particle of the same size, same shape, and different chemical composition could have different health impacts. And right now, the metrics that EPA uses is mass. The question is that, do particles of different composition also have different health effects? And we work with my colleagues in chemical and biomolecular engineering. We develop an assay using macrophage cells and cardiomyocytes, and we expose these particles to the cells. And the reason is that these particles are generated in the lab, so we know their composition really well. And if we go to do ambient measurements, we also have all these instruments that allow us to get more understanding of the chemical and physical properties of these particles. And we're very interested in linking the composition of these particles to the cellular response. And as for now, we're developing a more, I would say, high-throughput assay with another colleague in chemical and biomolecular engineering with microfluidic device. So a lot of this work previously was done on 96 well plates, and right now we are developing this single-cell microfluidic device that allow us to look at the response of each cell when they were exposed to these aerosol particles. So I would say that the chamber studies, the ambient studies, and the health studies are kind of the three major areas of my group. And some specific projects that we have been working on in the last couple of years include how emissions from human activities, such as sulfur dioxide from power plants, nitrogen oxides from cars, and also ammonia from agricultural activities will interact with the emissions from trees to make aerosols. And we call this anthropogenic-biogenic interaction. And a lot of my colleagues behind me also work on this topic. And another topic that we're working on is how the wildfire emissions got transformed in the atmosphere to make particles. So if you read the news, there are a lot of news about wildfires everywhere in the world. So the question is that once these compounds got emitted into the atmosphere, they do not just stay as VOCs or semi-VOCs. They actually got transformed into particles at some point. So that's another topic that we are working on. And we also have a project that looked at sensor development for measuring air quality indoor and outdoor. So right now we have a little project with someone at Georgia Tech. So those are kind of the projects that we have. So I'll pass this to Rodney Weber.
Okay, I'll use that one. Okay, good morning. I think Sally basically covered everything. I am an experimentalist. I actually am in the Earth and Atmospheric Sciences department here at Georgia Tech, but my education is a mechanical engineer, but I do atmospheric chemistry. My approach is essentially I build instrumentation and then we deploy them in field studies, the kind of thing Sally was talking about. So I'll give you some examples of what we do. As Sally said, wildfires are a big issue now in terms of air quality globally. They're not only an issue for human health studies, but they're also an interest because they affect climate itself, because a lot of the species, particularly the aerosol particles, scatter solar radiation and absorb solar radiation. So one of the new things that people are finding about fires is they produce a lot of black carbon, which is the soot you, for example, see from a diesel engine or something like that. But there's also now colored organic components to the aerosol called brown carbon. They look brown or yellow because they absorb light preferentially in the lower visible UV. So it turns out that we were involved in a NASA mission, for example, an aircraft mission. They have an old DC-8 aircraft, which they instrument. Greg Huey, who's not here, was also on this study. And they flew this airplane from the North Pole, essentially, to the South Pole, down the Pacific. And every so often, they'd go up to 12 kilometers, and then they'd fly for about 10 minutes, then go down to the surface of the ocean, fly for 10, 15 minutes again, and go up and down. So they go up and down, stopping at various islands the whole way, pole to pole, turn around, South Pole, go up the Atlantic Ocean to the North Pole. And they did this in 4 seasons. So our goal, the overall NASA goal was to get a global picture of emissions. It turns out that fires globally have a large effect on the aerosol concentrations. And one of the components is this brown carbon. And so we had an instrument that we built specifically to measure brown carbon. And we found that it had never been considered before because people had not detected it. It's at low levels. People focused mainly on soot as the absorbing aerosol. And it turns out that it's about 25% of the overall absorbing aerosol. Fires from the Amazon, Africa, China, Indonesia, Asia in general can travel the smoke can travel long, long distances. So you can see these plumes in the middle of the ocean from long distances away. So we look at the evolution of that aerosol and how it affects climate through its optical properties. I'm also involved in a study in Fairbanks, Alaska that's coming up soon that's also related to fires. But there, the fires are people burning wood in Fairbanks in the winter. And Fairbanks happens to be one of the most polluted cities in North America in the winter because everybody is burning wood and they don't generally have very good wood stoves, very efficient wood stoves. So we're looking at the health effects of these aerosols in the community. And even in Atlanta here, I was involved with a study with Ted that showed that in the winter, you don't think there's a lot of biomass burning around, but biomass burning is becoming important because of climate change, more burning, and the other emissions are controlled. So emissions from vehicles are going down, so biomass burning power plant emissions are going down. So the end result is that we found in Atlanta, we developed an assay, something similar. Mine was a chemical assay. And we looked at the toxicity of the aerosol with this assay. And in Atlanta, actually, in the winter, it's a significant component. Biomass burning is a significant component of the toxicity of the aerosol we breathe. Another example of what I do is we use thermodynamic models with colleagues we collaborate with, and we look at, for example, the pH of the aerosol, the acidity of these particles you're breathing. It may not be, this is not well known, but the actual aerosol acidity is very high. It's almost like battery acid. It can have a pH between 0 and 2 in the southeastern United States. That has interesting properties that people have in the past not really considered, because it mobilizes metals that are in dust, like iron and copper from brakes from cars. That is, it takes insoluble oxides and makes them soluble forms, and then they become very reactive. When you inhale them, they can interact with chemicals in cells, and they produce strong oxidants. And this is thought to be this is a new paradigm of thinking of what causes the toxicity of the aerosols. So that's another project I'm working on. And so generally my approach is we develop instruments to measure properties, we apply them to field studies, and try to come up with the effects on climate and human health. That's it.
All right, thanks. So I'm not Greg Huey. I'm Jen Kaiser, newest member of Team Air Quality here. I'm in Earth and Atmospheric Science and Civil and Environmental Engineering. And like everyone else here, I'm interested in understanding how anthropogenic emissions or climate change influence air quality. And specifically, my sort of subset of the topic is looking specifically at those VOC emissions, those volatile organic compounds. So that's any reactive hydrocarbon. And these are the precursors to the photochemical smog that we see in Atlanta, to the ozone, to the particles that Sally and Rodney study, and Ted as well. So I really want to understand what VOCs are emitted and then what happens to them after they're emitted. And in general, VOC emission inventories actually have about a factor of 2 uncertainty globally, and an even higher uncertainty at a local scale. And those are the same emission inventories that our air quality models are built on. So that uncertainty propagates through to our understanding of air quality at any given location. And when you think about how those VOC emission inventories are built, it makes sense that there's so much uncertainty. So there's a high amount of spatial and temporal variability in these emissions. There's chemical complexity as well. VOC is a huge family of compounds with thousands of different molecules in it. And then more specifically, the largest source of VOCs is actually the biosphere. Even in urban areas, the biosphere contributes a large portion of the total amount of VOCs. So the EPA is not going to measure every tree, right? So we can't really constrain those emissions as well as we can other sources. So what I'd like to do is to map VOCs in a given region, specifically Atlanta right now, and to understand what happens to them. Rather than go out and measure every single VOC, one of the techniques I use is a product-based perspective. So I use formaldehyde. And formaldehyde is the simplest aldehyde, and it's formed in the oxidation of nearly every VOC. So no matter what you start with, that carbon at some point is likely going to end up, some of it as formaldehyde, on its way through to CO2. And then formaldehyde itself is oxidized or photolyzes to form the OH radical, which propagates this chemistry. So it's sort of this linchpin in the middle that you can use to understand emissions and also how that oxidation process is happening. So the EPA does measure formaldehyde, but I would say they don't do it very well. Their measurements are typically multi-day averages, and they have interferences in polluted conditions. So part of what I do is instrument development and deployment also, specifically to do sort of low-cost and reliable, robust monitoring for these sort of long-term stations. So we've got some formaldehyde monitors now. There's a near-road site at Georgia Tech's campus where we've put our first one out there. But if the idea is sort of long-term, low-cost sensing, really the gold standard is remote sensing. So that's satellite-based interpretations of air quality. And our satellites have gotten better and better. And I view my work sort of in the context of this evolving satellite capacity. So about 2 years ago, our satellites measured formaldehyde and NO2 and ozone at about 25-kilometer spatial resolution. Last year, we started to get 7-kilometer resolution. And then in the next 2 years, we're going to have 2-kilometer resolution pictures of formaldehyde and NO2. And those pictures will be every hour rather than every day. So we're going to be swimming in data if we know how to use it. And part of what I'm excited to do is build a ground-based validation network to make sure that the data we're seeing from the satellites makes sense with what we're seeing on the ground. And then once we've sort of made sure that those satellite measurements are correct and we know how to interpret them, is to use them in global chemistry transport models to do a backwards analysis. So we know how much formaldehyde we see, we know sort of the chemical environment, and then we can back out what those VOC emissions are. So the end goal of all of this is to develop more predictive, more accurate air quality models with lower uncertainty. And we take both an instrumentation approach, sort of with this long-term monitoring, as well as specific field campaigns, as well as global modeling. And with that, I'll pass it to Ted.
Great, thanks. I'm Ted Russell. I'm at the opposite end of the spectrum, as I am I think the oldest member of Team Air Quality at Georgia Tech, which it's great to actually be part of this, is that you're actually only seeing a fraction of us, and that there's a number of professors who couldn't make it. And it just goes to attest to the depth and breadth of our group. And what I'm going to talk about a little bit is sort of a different direction, in that I'm also the Georgia Tech co-director of a National Science Foundation Sustainability Research Network on healthy and sustainable cities. And the real key to that title, so far as my work goes, is the healthy part, in that what I do is really link infrastructures and sources to health. And that, as Sally said, air pollution has a range of health effects. And actually, it's one of those that's totally underappreciated, in that you may not realize, but it's one of the top 10 environmental risk factors that essentially globally as well as in the US. As it turns out, even in the US, it ranks up there with smoking and drinking as a risk factor. It just sort of sits out there. You know, you don't realize you're breathing all these particles and gases, and your lungs, they're there to pick up these things, and so they have these elevated risk factors. They can even get into your brain directly. So there's been a lot of work looking at how to link air pollution and health, and this is the type of work we've been doing. We work very closely with Emory to look at linking various sources to their health outcomes, be it cardiorespiratory disease, neurological disease, dementia, et cetera. And that all of these links appear to be stronger and stronger established with time, as we've been able to develop our ways of linking sources to health effects. And so what we've been doing is looking at better ways to analyze exposure and quantify exposure. And then our colleagues at Emory take those and work with them to figure out what the relationships are. And that was largely in part, we had a EPA health center to do that work, but it continues on with our relationships. One of the other things I just wanted to bring up is we've heard a lot about fires, and that's one of the real strengths of Georgia Tech, and we started doing this probably 20, 25 years ago. My colleague, Talad Odman, has a poster out there where he's leading the work in Georgia to do predictive air quality of the fires and health. And this is work that follows on. Michael brought up yesterday that we've been doing forecasting of air quality for Georgia since I guess it was 1994 or so, before the Olympics. And that's morphed into also looking at being able to do predictive air quality forecasts for fires and health. So that work is continuing to grow, and we're doing it throughout the Southeast now. One last sort of example of the type of work we're doing is that as part of our National Science Foundation work, we were in India looking at actually how biomass burning was impacting air quality. And when we were in Agra, we saw that there were all these scaffolds up around the Taj Mahal. And what they have to do is they have to clean the Taj Mahal all the time. And so one of my students looked at this, and what we saw is that the biomass burning impacts not only the Taj Mahal, but also the air quality effects. So what he did is he showed how much the biomass burning was depositing on the Taj Mahal, but also that it was leading to about 700 excess deaths per year. And that gave extra motivation to essentially, for the Indian government, to start putting controls on biomass burning, which they did. So we were able to really affect change in that way. I'll also say we don't only look at human health, we also look at environmental health, as we've been looking at agricultural runoff and emissions and their impact on air quality and water quality and forest health. So with that, thank you very much.